Oh, really? Oh, I got a thought actually.
We have some.
I like this album.
Because every time he says this is great,
Welcome, everybody. I'm glad you found your way to your seats. Thank you to Sierra Ventures for having us today. I'm Carla King. I'm a back-end engineer at Civil Maps, where I get to work on a ton of really cool projects, including developing our 3D semantic geofeatures, working on our data processing pipeline, and most recently, routing. And I have to admit that when I signed up to work on the Civil Maps team, I did not know routing was going to be a part of it. And the reason being that it's something that we kind of take for granted this day and age, if you're like me. And in order to illustrate this point, I'd like to pose a question to you all. How many of you had to plug in Sierra Ventures to get here today? Into Google Maps, Waze? Looks like a few of you did. Okay, well, let's reframe the question. How many of you had to plug in into a navigation system how to navigate to work this morning? Apparently 2 people. Are you guys, is it your second day? The point I'm trying to make here is that it's something that AVs don't have the luxury of just sitting down and navigating themselves. It's human intuition at some point when you get into a vehicle and you know your route if you've driven it before. But this is an absolutely critical thing that an AV needs in order to get from point A to point B. Even if it has traveled the path before, it needs a route. And here to discuss that topic today, we've got a range of perspectives from 3D robotics, or excuse me, Aqua OpenRVO company that actually they're going to give us a perspective from the point that they're going to need routing in the future in a different environment, underwater. We've got an automotive investor and somebody working in manufacturing. And these individuals are, we have Charles Cross. He's a recent East Coast transplant, now working at OpenROV and developing underwater robotics. I'm just going to give a brief introduction and let you guys speak a little bit about your projects in depth. We also have Robert Seidel, and he's managing partner at Modus Ventures and CEO and founder at Real Time Video Systems. And John Mullen, a researcher at Ford Motor Company, working in automated driving. Okay, yeah, I'll have you all just talk a little bit specifically about your projects.
Charles Cross with OpenROV. So basically, we make low-cost underwater drones. We're trying to be kind of like the DJI of underwater. we have a strong focus on pushing connected exploration. So we are focusing on the internet, the ability to do internet control and live streaming of your robot stream across the internet anywhere in the world.
Robert Seidel. I'm with Motus Ventures. We are happy to be an investor in Civil Maps, and we basically invest in early stage companies that do autonomous navigation or the infrastructure around it, sensing, mapping, things like that. And I'm actually a last minute replacement, so if I sound less knowledgeable than the other guys here, excuse me.
And my name is John Mullen. I work for Ford Motor Company out of our Palo Alto office. My focus is mainly on geographic information for level 2 systems.
Okay. All right, I'm going to just stop using that.
Yeah.
So the very
don't think
first
I'm on.
question that I'd like to pose to the panel is, I've often heard about 5 different levels of routing, and those thinking of those as different stages. And one thing about routing for AVs right now is that everything is very much, or some portions you have figured out, where other parts we're still developing, and kind of everybody's just innovating right now. So I wanted to bring up these 5 different levels and maybe have you speak to them and talk about whether they're unknowns or if there's something that kind of the industry is already starting to set standards. And the different levels are perception, mission planning, behavior planning, trajectory planning, and vehicle controllers. So can you all speak directly to any of those different stages of route planning and exactly what level of development?
Yeah, sure. So perception is still very much an unsolved problem, especially when it comes to fusing sensors together, their various signals together, and trying to make that package cheap enough that we can actually deploy it on the road. If you look at a lot of the Google, a lot of the times that they've had to intervene and and sort of rescued their car, they mostly write it up as perception discrepancies, which you can sort of interpret however you want. So that is not a solved problem. Vehicle control, we've got a pretty good understanding of. It's a matter of reducing the amount of compute it takes, so that we leave room for other things. And then, sort of path planning in cluttered environments is something that a lot of work has gone into. It's still not really mature, and the compute for it is still very expensive.
If I may, I'll just rephrase the problem, because I've heard it in a different way, and it maps to what you said. Obviously, you have a sense, plan, act type of triad of things in robotics, and perception goes under the sensing, and there's a lot of activity at the moment in sensing. We have new sensor modalities, especially in cars, with the LiDARs coming along, but we need sensor fusion, which is a new type of processing. And then on the actuation side, there's very mature technology to do things like emergency braking and path planning to reduce collision impact and so forth. In the middle, though, the planning, that's the way I think you called it behavioral and path planning. A lot of stuff is happening there, and a lot of data inputs actually play into that we haven't considered before. For example, synthesized data inputs such as the cars around you. There's a certain flow of cars around you and the car in front of you. People navigate by driving behind the truck on long streets, even they can't see anything else because they trust the thing in front of it. So that's just another sensor input. And of course, maps play a huge role in planning there. And in that middle planning segment, people often divide it into 3. There's a strategic planning, a tactical planning, and the reactive planning. And the strategic planning is more the point-to-point, what you do in Google. I want to go from here to home, and it does a route for you. That's pretty well understood, although there are things getting improved there as well, like Uber is doing. The tactical planning is where you do lane-level planning, so not street-level planning like the strategic planner, but lane-level, where you go, I need to do an overtake maneuver. That means I've got to go in the lane left of me and then pass, or I need to stop and then turn right, or I need to like exit the freeway. So those are lane level plans. And then I think that's where trajectory and path planning comes into play the most. And a lot of experiential data is being collected by companies like here for that purpose as well, to help plan where the risks are so that you don't overtake in a place where people are coming into the freeway, for example. And then the reactive planning is basically collision avoidance, which is well understood, I think, by companies that do that today. But so those upper two level, the strategic and tactical planning is, I think, where most of the activity, both on the input side of data and on the algorithm side is happening.
So in underwater, we actually kind of have it rough compared to most other above water spaces, in that we're still stuck at the sense stage. In underwater, electromagnetic waves don't travel underwater very well, more than about 10 centimeters. So we don't have GPS, we don't have connectivity to the internet, we don't have any of these kind of technologies, and we're usually confined to a small space, which is constrained by cost. So when it comes to finding out, even coming up with a simple state estimation, we're pretty challenged in that area, mainly just cost and also what sensors are actually available. So lacking electromagnetic sensors and communications, we typically turn to sonar. The cheapest side scan sonar system costs $8,000 to $10,000. So we are very limited. And right now, our drone that we're developing is pretty much limited to a 9-axis IMU, a depth sensor, and a camera. So we're kind of trying to come up with like clever ways to get around those limitations and come up with new cheap sensors, new methods of sensor fusion. And I'm kind of have the feeling that in terms of strategical, tactical, and control development, most of what's already been done in the industry is suitable for most of the needs that we have underwater. And there's probably like a lot of situations like with complex navigation without a tether through tricky environments like underwater cage and whatnot that statement probably doesn't hold true for. But for most of the control situations and planning that you would do with underwater drone, basically surveying places, making maps, there's not a whole lot of complicated planning that you have to do. So I think like kind of the current technology would suit us for that if we only knew where we were.
You should say how much your drone is.
So most of the commercial drones, the underwater drones, cost anywhere from $20,000 for the low-end one, and most of them sit around the $40,000 to $80,000 range. And ours sells for we have a kit that's $900, and our new vehicle is $1,400. So we're trying to kind of compete the same, making it available to consumers and available to people in general.
And if you look under your seat, there's a ticket, and each one is a
You get one.
You guys hold the mics up closer to the back.
Sorry.
Thank you.
So, thank you. I want to switch gears and talk a little bit about, again, industry standards, specifically when it comes to technology. You guys have mentioned different sensors. So from the technical standpoint, the sensors that you're using, what's industry standard, and also for technology like OpenStreetMaps for providing the input information for route planning. I've heard a lot of companies are gravitating towards OpenStreetMaps and wanted your opinion on that, and if you think it's a good thing that these standards are being developed.
Talk about OpenStreetMaps from Monterey Bay.
So I really love OpenStreetMap. It is fantastic for prototyping. The concern we would have with standards is going to probably be motivated around something like ISO 26262, which goes and specifies basically how you evaluate risk and how you really talk about safety. And it comes down to the likelihood of something happening, how exposed you are, and how well you would be able to control it if it did happen. So in the context of a map, what you would be talking about is how bad is it if we don't know that there's a fire hydrant somewhere? It's probably not a big deal. Right, what's the risk involved in that? If we don't know about a place where merging traffic is happening or a place where construction is happening, you're exposing more vulnerable road users. So those are the kind of standards that I think we would worry about are, the accuracy of the maps and probably on a sort of asset by asset basis.
Well, I think the maps that we are talking about today, like Google Maps, Apple Maps, OpenStreetMaps, those are all great for the strategic level route planning, going point to point, the topology is defined. they're not precise enough to drive a self-driving car with. So we need a whole new class of much, much more detailed maps with information that's specifically made to talk to a machine rather than to a human that, where you actually try not to have all the detail in there because it would just be too confusing. For a machine, you need to have all that information in there. So the map is actually a very high precision but high latency sensor for a perception system. And we like sensors, and so one of our companies is actually Quanergy that makes a solid state LiDAR for cars that's very small, very cost effective, and it'll change the landscape of what people put on cars. A Model S-Class has, I think, 5 radars, 3 looking front, medium, short, and long range, and then 2 out the back. A bunch of ultrasound sensors all around for short-range parking and collision avoidance. At least 1 camera, maybe a lot more, I don't know. So there's a lot of sensors on these cars, but there are also sensors inside the car that don't look out, like the GPS, the IMU that senses how far you've moved acceleration-wise, and then other sensors that companies like HERE will provide, such as, or actually you, Mr. Wilson there provided, his company provides, like average driving behavior over time for most people in the right lane on that piece of stretch of road. Over time. And so these are all useful input sensors. And then a synthesized sensors like the thing in front of you. I don't think much of that is standardized at this point. And even the map formats for the self-driving stuff are not standardized. There are a few attempts to go out there, like TomTom has a thing, what is it called? Help me out here. TomTom, what is it called? Road DNA, thank you, which is a side-level hash format. HERE has its HADMAP format. The National Driving Standard in Europe, pushed by the Germans, has its own database. It's a database and updating format. I think it's very early stage, so it's nothing is standardized in that world yet for the high resolution, for the highly automated driving maps. So I think there are opportunities to contribute to making a change.
Do you see that being an issue moving forward? The fact that nothing has been standardized, are we going to have to reach some consensus as an industry how these AVs are actually ingesting the maps?
I think it's more an industry question, right?
Yeah, I mean, we would expect some very consistent, very stable interface. I think it is kind of early, and there's only so many ways of describing where something is. The issue I would see is if we all had different descriptions of the topology of the roadways, and that sort of thing, where things are connected and what that looks like. But we're all talking about the same thing at the end of the day. I think you should pretty easily be able to cross between mapping formats.
Yeah. I think there's something called OpenGIS that has made an effort to do that standardization between the data formats for maps and other data. There are some efforts in open source to do that.
Yeah.
And I think most
Yeah,
of the
Open Drive
yeah.
as well. Yeah.
Okay, the next question I want to pose to the panel actually kind of brings together the past few panels that we have. And that's how we actually integrate the technologies of building 3D semantic vectors, the geo features that you see in space, and the technology of localization and route planning. And just to give you some context, localization is the technology that uses computer vision to assist and augment the GPS on board of the car and identify its exact location on the Earth's surface. I'll stand over here. And then we have 3D geo features, which are they're the center lines and the actual lane edges and their relationship between the two, and the signs and signals and where they are in space. So how do we combine those two pieces of technology to interact with route planning and inform route planning?
Well, I can't really speak to data on the lane changing and stuff like that, but definitely I think SLAM is going to be one of our critical pieces, simultaneous localization and mapping, the techniques for how you can actually create a map of where you are. Is going to be actually pretty critical for us going forward and how we're going to do any kind of underwater autonomous planning. Since our main sensor is a camera, That's where we're going to get most of our source of data. And even then, it's still challenging because in most bodies of water on the Earth, your visibility is less than 5 feet. So, but we've definitely got one of the people in the community that we're working with. He's doing his PhD, and he's working in underwater SLAM, and he just came up with finally a working prototype. He did a test in a pool, and he was able to use one of our ROVs to create a SLAM model that actually works. So one of the things we're looking at with our new model is to try and incorporate SLAM technology to do things like exploring new areas. And also doing mapping. So we've got one aspect of mapping where we're going to be flying above features in relatively clear water and doing photogrammetry, taking downward-facing snapshots and then stitching those together into a mosaic, and also 3D models. And they'll be using the forward-facing camera for creating very local SLAM maps in terms of like objects around us that we might want to follow or track to, and also navigating through one potential use cases like in a nuclear plant, being able to use the ROVs to like traverse like through some of their water tanks and do inspections on the inside of structures like that. So SLAM would definitely be a useful feature there. So creating a kind of software technology, software features is important to us.
Actually, I've got a follow-up question. Can you talk a little bit more about SLAM and what it is exactly?
Okay, so SLAM is kind of a combination of a few different things. It stands for simultaneous localization and mapping. And basically what that means is you've got a lot of sensor data coming in from your various sensors. You're fusing that sensor data together to get an estimate of where you are in the world, and you're also using sensor data about external objects to create an estimate of where other things in the world are relative to you. And so you have a map of what's currently around you based on what sensor data is coming in. You also have the map that's been created in the past of where you thought things were, and there's probabilities associated with based on like how good of sensor data you think you have of what the probability is that where you are right now and what the thing you're looking at now is relative to what you saw in the past. So it's basically just a technique for creating a map and localizing yourself within that map.
Thank you.
What was the question? Yeah, that was a great explanation, I think. What was the question?
It was
I'm consumed by his SLAM
it's
explanation.
yeah, me also. It's integrating localization with the 3D semantic geo features, and how to allow that to inform the route planning. So it seems like those two are kind of preceding. You need those two to be really accurate and precise before you can even talk about route planning.
I have to admit I don't know too much about that. To me, localization is a separate input to where you are within a lane is necessary, but I'm not sure what the feedback is between the map and your own localization. They might be derived completely separately or from the map, I guess.
Okay.
One of the issues is if you use just what you see for localizing, like Mobileye, for example, is a maker of a camera and software behind it. They do things in the Tesla. There's a camera, the autopilot, and the lane change warning, and they're done with that system. And so they look at, for example, the lane markings, and if you drift too close to a lane marking, it'll give you a lane change warning.
Okay.
That's done using what you see on the ground, but if everything is invisible because you're in a jam on, as you usually are on like 85 or 95 here, then you don't see the road markings, and so you need to localize yourself using some other means, and inertial is probably not good enough over the long term, and so one way people are doing that now is looking at things in 3D and trying to figure out where you are with respect to the 3D landmarks. Wasn't a very cogent answer, sorry.
No.
I can kind of add on to that. So when I was working at NASA in Langley, Virginia, there was one of our techniques that we were like trying to experiment with drones and 3D localization was if you didn't have GPS, if you're in a GPS denied environment, using 3D data about the place you're in, so taking a camera view, looking out like this window right here, and using salient features from each of the different like the power lines, rivers, and other things that you can see in the image there. You can map those salient features to like a database of like a known things in a map, a geographical map that might have those very prominent features mapped in it that have GPS coordinates attached to them. You can triangulate off of those positions to know where you are and not even need a GPS coordinate. So.
Okay, so now you've triggered something. That is actually a common problem. GPS denied is not just a military problem, it's also a problem when you drive around in a city, in a tunnel, in a parking garage. You don't have GPS there. And so what do? How do you figure out where you are? And the landmark detection or salient feature detection is important, but if you just do that optically, there's a lot of change when you just use video, for example, to do detection of where things are that might be important. One of the things that changes all the time is lighting. Lighting during the day and shadows that are cast. That makes very variant pictures. And so making two the same so that you can say, oh, I'm here, is very hard. And likewise, when you have vegetation that changes over time, in remote sensing, that's a common problem. Anytime you look from above and you look at a field in the winter and the summer, it's really hard to tell that it's the same field. And so the advent of good, cheap LiDAR is very important, because LiDAR is a technology that measures depth without you having to do a lot of processing, and that's independent of what the incident light is. So that's useful as a fusion technique for deriving these landmarks or salient features.
Yeah, I think it's an interesting question, because you want the semantic side to sort of add context to what you're doing, but at the same time you need these hard numbers at the end of the day to tell you how many inches you're gonna be from the curb. So yeah, in terms of like drawing it as a boundary diagram or a block diagram, I think it's very difficult, and you know, the solution is going to be something more of a conversation and a back and forth between the map, the routing, and the localization, so that, you know, they sort of form a holistic kind of picture of the scene and where you want to be.
There's also information that a sensor itself can't really easily derive sometimes. Like, there may be a bunch of traffic lights over a large intersection, 3 lanes, and there are only 2 traffic lights. And now the car has to decide which traffic light it has to look at, whether it can go or not. And sometimes that's just not easily derivable. And so the best thing is to get that from a map. That's maybe derived with a lot more processing or a lot better sensing, or even other metadata that comes from the city or somewhere else. Same with traffic signs. And lane level data is also important to know ahead of time.
Yeah, and I think I've got a good follow-up question, because I think that we keep alluding to this, but I would like to hear you all talk a little bit about the navigation that we know now, Google Maps as a normal everyday user, and the navigation that is needed and the detail that's needed for navigating and routing an AV, and how they're different maybe at a high level or a more technical level.
All right.
Google Maps. So you kind of have to debate first what exactly you think is in Google Maps. But the things that we're familiar with are very much at the navigation level. It's meant to tell you what everything looks like, and you're doing all the reasoning to get yourself through, and in some places just sort of winging it and adapting to things that might not be the way it said it was, or maybe you drive by something a few times accidentally and that sort of thing. The maps that we'll use for highly automated driving are going to be a lot more detailed. They're going to have to sort of encapsulate nominal vehicle trajectories. It's not going to be good enough to just say this is the street and we think it's this wide and we think this is its center line. It's going to have to, you know, be detailed enough that you can go through and do that localization, you know, and that route planning on it.
Yeah, mapping it back to my original, you know, the 3 levels: the strategic routing, which is the road level routing, which is where a router says, you know, I know the road network topology, I want you to get from here to there, and it's basically an optimization problem. And the road level router can make remapping decisions in the middle, like when there's a traffic accident, and you know, you get that data down in live, real time, and then it says, okay, I'm going to reroute you. But it's road level data, very coarse. And even the roads, when you look at these maps today, they're polygonal. they're not trying to be super precise. Part of it is to reduce the amount of data that you have to send down, but part of it is for visualization. You don't want every nook and cranny in there. The second level planner, the tactical planner for an autonomous vehicle, requires much more detailed data. It requires basically lane level data. And so when it says 92 freeway, that's what would be on Google Maps or OpenStreetMaps. Sometimes they have a little bit more, but they certainly don't have the geometry of the individual lanes, or what we call about, you talked about semantic maps, the meaning between the lanes. So, you know, maybe that's just a high occupancy lane, so you can't just cross over, or this is you mustn't overtake at the moment because there's a double yellow, or all these information between lanes is important to know for an autonomous vehicle trajectory planner on a tactical level. I think the map information becomes less important on the I want to avoid crashing level, the lowest level, the reactive planner, because there you really do obstacle detection and avoidance. The map is less important. But even on a very high level, Google Maps and Apple Maps and these things can become better once we know about 3D, when you know about how high your truck is and how high the bridges are, or the trees when you go by. You may want to avoid getting into a situation like regularly happens today, where you go into a tunnel and you start scraping things, or the tree hits you, or things like that. And when you have a real 3D map with obstacles in 3D, it will help to know that. So even on the strategic level, I think better maps can improve things. But the heart of the matter is in the tactical and the semantic map provided there.
I just kind of want to stress when we interact with maps normally, we're typically thinking in 2D or 3D as humans. But now we've got so many forms of sensors, so many forms of like information we can extract from those sensors. With just a camera alone, you can extract thousands of different layers of data for one spatial area. And we have to start thinking in terms of these maps as not only being spatial, but also, like you said, light levels change over time of day. So now they're becoming spatial, temporal, and there's different levels of metadata in there. So I think one of the key things for us going forward for doing the strategical and tactical planning is getting smart about how we use these different levels of map, basically resolution. So one example of how to describe this is you can have do a LiDAR scan of an entire city, and it's trillions and trillions of point clouds data. And when you want to do route planning for, say, a UAV, if you were going to deliver a package like your Amazon or something, you don't need to worry about the world at a point cloud resolution level. Having just a basic 3D geometrical view of the world can help you do your course route planning. And then, but still, that lower level of data is important. And it's important how we can know what data you need to have when you do any particular kind of mission. The point cloud data might be useful when you're trying to navigate the drone through the duct to get into the warehouse. So I think definitely being able to intelligently create these maps, segment them into different kinds of categories, and know how to use that in real-time strategic planning and avoidance and control is going to be important going forward.
I think you make a good point, namely that the point cloud data is extremely voluminous, and you need to reduce the amount of data so that you get the salient information out of it. Because even in the long term, we don't foresee the ability to just stream everything up through the cloud from every car. It's just not practical. And so the question is, what do you stream up if you detect differences? And also to reduce the amount of processing that you do locally, you have to have kind of the high-level information rather than the raw information.
I've got a question that kind of piggybacks on that concept that you just brought up. So when you're given a route and you start up your car or your underwater robot, are you going to actually download just your route, or are you going to download a contingency plan, just in case you need to reroute yourself? What happens if you encounter an obstacle? Do you just stop and turn off? Or do you actually have access to a database and can dynamically generate routes on the fly?
So typically in both the aerial drone area and also underwater drones, typically the approach that you'll take is, and this is probably similar for cars as well, is to when you're in an area and you have connectivity to whatever database has this information, you download, you have your rough, I want to go from A to B, and you download all of the data that you think you might need, potentially all the data for that area, and a buffer around that as well in case there have to be contingencies. You create an initial plan. This is like your strategic planning level. You make an initial plan. You start to execute that, and with all the data that you have. And as you go, this is like the sense, plan, act. You start acting on that, and if you encounter something that's in the way of your path, you've got two types of situations. Either you have an impassable object, like say you're trying to navigate a robot through a building and the door is closed that you expect to be open. You can try and like explore, start going into exploration mode, deviate from your path and try to find a new way to it. Or you can look at the map that you downloaded and replan in the building. But there's also dynamic types of things that can get in your way, like a person walks in front of your path. In that case, you're probably not going to be like replanning a path through like the entire map data that you downloaded. You're just going to be doing a dynamic avoidance of whatever is in front of you at the time. And so you have to like be able to distinguish what's a dynamic and static obstacle and that sort of thing.
Are you doing route planning today in level 2?
No. Not. No, not so much. No. Yeah, level 2 more. More comes down to lane keeping and that sort of thing right now. A lot of people think of level 2 as being strictly on the highway, though. It's not. The actual definition comes down to what is the driver's responsibility and what is the vehicle's responsibility. And in that sense, we can keep extending level 2 for a while still. And that's when use cases will start to get a lot more interesting, and route planning will get involved. But these lowest level route things that happen on like the 2-second time scale, you have to do something, right? If all of a sudden you recognize that a deer jumps out in front of the car, you have to do something. But a lot of it is still motivated by the user, dictated by the user. Yeah, as far as the sort of high-level mission plan goes.
I think route planning is very dynamic in the innermost loops because the map is a static thing. It's very precise, but it's almost always wrong because the things change in the real world. And if you look at any map there, you will always find errors unless you collect continuously, which is very hard. Although we're getting better at that, I think. And so the innermost route planner constantly has to adjust for things that change. And as you are in traffic, there are other cars, there are maybe obstacles, there may be accidents, there may be a traffic jam. So you constantly have to adjust in real time, even on that very last level. If you do an overtake maneuver and you see a car coming at you, well, then you have to cancel that overtake maneuver. And so the route planner has to basically change its plan continuously. And I think the map in that sense is like many other sensors, and you have to attach a level of trust to the map, which will probably be annotated by having some sense of age in the sensor. Like other sensors can qualify themselves. If your LiDAR or camera has a bird poop on it, then it has to be able to tell the rest of the system that you can't trust either the whole sensor or part of the sensor. And I think the map has to have something similar in there.
Okay. Cool. Did you have anything to add there? Because I want to shift gears a little bit and talk about government and the role that government is playing in, I guess, both the various industries here represented. And I don't know, actually, if you guys can speak too much to this, but what role is government playing in shaping the standards of the industry? What influence are they having on the AV environment right now?
So for the most part, when it comes to underwater autonomous vehicles with the government, you just don't know. That is like the one frontier of like military technology we have like in the United States that just it stays all under lock. Our nuclear subs, everything's under wraps with that stuff. So there's really not that much in the way that we have been approached by the DoD and other organizations for doing like mine sweeping applications and that sort of stuff. And they're really interested in making sure that American companies are creating this technology. So I guess that's one way in which they are influencing the creation, innovation in the space of underwater research, is that they want to make sure that we stay on top of that. And so they're kind of interested in that. Otherwise, one thing that would really help in our space, and I guess in all of the spaces for autonomous vehicles, is having map data available to us and make it easily accessible. I think, what was the name of the agency I'd asked you about?
National Geospatial
The National Geospatial Agency. They create maps. There's bathymetry data for like mapping the ocean floor. A lot of it comes from like the 60s and 70s. We've got much better sensors these days for mapping that sort of stuff. And there's a wide variation in how the ocean floor is mapped. And considerable, like a majority of the portion of it has not been mapped. And most of the ocean floor we can't map using satellites in space because you can't see through water. So having the one way the government can shape that is like they can make all this data which is technically available to the public, but they don't provide a standard API or way to access it and use it. So that would definitely be one way that it would help us to be able to access that. And one of our goals at OpenRV is, since everything's internet connected, all the data that you can opt in or opt out, all the data that you collect with your robot and the maps that you create, we hope we can like distribute that process and create a public database for that type of information. And it doesn't have to stop at just underwater drones, but hopefully that technology can be used for creating public data sets for that purpose and doing routing off of that information.
Open seabed.
Open sea.
I've got a follow-up question. Is it what the data that they make available? Is it in LiDAR format, or is it a static, an image? The bathymetric maps that you're
I
referring
think
to?
it's basically elevation profiles,
Okay.
like point data, what the depths are. There's different ways of doing that. Sometimes they just take like, this is like old school data where they would just take I forget what the technical term, but they put a weight on a string and they lower that down to the bottom and they take a measurement. A lot of our bathymetry data is that, and then as things got more advanced, they started using satellite imagery for shallower water. And there's also techniques you can use with gravitational effects of the Earth, and like a mountain on one side of the Earth will cause a divot, and you can kind of tell certain elevation changes that way. And then of course you also have like sonar mapping. That's really expensive, and it takes a while to map. The ocean's huge, so.
I'll let you talk about the car-related stuff. Maybe I'll just give a quick note on the FAA, because we also have a drone company, a flying drone company investment, and there the FAA gets very concerned because they don't want people to fly, however small a drone is, into the turbine of a jetliner, because the risk amplification is enormous in that case. There we have at the moment a very few tools in terms of mapping. There are some companies trying to do that and to add kind of a semantic level to the map in terms of airspace vertically, as well as protected airspaces around military bases, airports, government installations, things like stadiums, so that a drone operator wouldn't have to guess or know or risk it, but would just know from, the drone was basically say, I'm not going to go there. In this case, the manufacturing and the pricing of drones has far outpaced what the FAA can do. So the FAA is trying to catch up with that stuff. And we are getting regulations now that will make it possible to fly legally, but there's a whole catalog of things that you have to adhere to. And in the car world, it's moving slower, but I think there's a whole lot more regulations.
Well, thankfully, that's actually not my department. We do have counsel that is very actively talking to NHTSA. NHTSA has been holding hearings about everything, and for them it's all about saving lives. So they're very committed to doing a good job on that.
So does everybody know what NHTSA is? National Highway Traffic Safety Administration. But it is true, isn't it, that even for autonomous cars at the moment, it will follow the same model as for everything else in the car world, that the car makers self-certify to the best available standards within certain guidelines, or is that not the case?
I think that's still up for debate.
And what are the alternatives? Third-party certification?
Some sort of autonomous driver's test would be it. You could close a course and have them take a driving test, something like that.
To have who? Have who?
The cars.
The car.
Yeah.
Okay.
Yeah, I think what you'll probably find pop up in that area is like some kind of statistical model. Like there has to be you go through several of these tests and qualifiable of certain probabilities of things going wrong. Because that's the only way we can ever, with these computer programs that people write, software engineers are people too. They're always going to have flaws, and and so
we don't need those anymore. We do deep learning. We don't need them.
Well, see, even with that, you're going to have a statistical model of basically how how likely you are to keep things safe, because you're never going to avoid 100% of fatalities. That's just like an unachievable number. So there's going to be some kind of statistical threshold set for these, and how do you, because you're never going to be able to prove a deep neural network probably. It's an intractable problem,
Yep.
I think. So they're just going to have to qualify under some certain statistical threshold for safety.
Well, that's an interesting point, though, because we haven't really talked about the implementation technologies. But one thing that came up, and as actually a discussion with is John here? John Novak from Quantigy, he was the VP of engineering there. The whole risk framework and safety framework around ISO 26262, which is an automotive functional safety standard, applies to the techniques and methodologies that we use in typical programming and software engineering today. We have procedural programs, we have source code, we have if-then-else statements, we have Agile and Scrum and peer review and version control and Git and all these good things. And then come along, these guys with neural networks, and they say, look, it works much better than any of your stuff. And the ISO 2626 guy goes, well, I want to see which if statement you hit when you ran over the grandmother. And the thing is, the methodology and the tools expressed in the functional specification of ISO 26262 and in the risk specification of ASIL do not map to these new techniques that we're developing on the perception side. So I'm actually very skeptical for many years that the Sense Plan Act pipeline is going to be fully based on deep learning. I can see perception being based on deep learning, and then the rest, namely the planning and the actuation, is going to be done using techniques, traditional techniques, especially when we talk about actuation and ECUs that have hard real-time constraints and multiple redundancies. Your brake controller, when an alpha particle hits it, or when it gets too hot, or when it gets a little bit wet, can't just stop working and stop braking. There has to be redundancy in that. And those are really hard constraints, and I think they carry over in the planning as well. Somebody needs to know, it's like, if an accident happens, they have the black box data, and they go, well, why did you try to overtake at that point? You have to have that introspectability of the system and the accountability for the manufacturer or the supplier of that system, and essentially the coder to say, well, why did you put that in there? And that was a problem. We don't have that with these new systems that are admittedly very effective at doing what they do in perception. I don't think the government would allow, or the manufacturers would expose themselves to the risk of saying, well, we'll just go from sensing directly to actuation using neural networks, because these standards don't map to that at all. You're so lucky you don't have any of that underwater.
Yeah, but that's given time. Eventually, what may happen is we'll have a good measure from the traditionally programmed control loops and all that kind of stuff for what is the risk that's associated with these self-driving cars, what is the percentage of fatalities, how often do accidents happen. There may come a time when enough time has been spent developing these neural networks that the statistical probability that those systems generate is much lower, and then the acceptable risk from using those systems to actually control the vehicles may provide a better alternative.
I actually agree with you, but I think we're a long way away from that.
Yeah, definitely.
And simulation will play a huge role in that, because that's the only way you can actually try out some of these things in the real world.
Those are wonderful insights. It was not something I had previously considered. So it sounds like the government will still have to hold the AVs to the parallel parking tests before they get to actually hit the roads.
I should say there's at the end of this month, I think Joshua Schachter is doing a self-driving race event up at Willow. Anybody remember what it was called? Anyway, look up Joshua Schachter, and he will have, there's a bunch of people from Renovo and from Zoox and from Stanford going up there, and they're going to do exactly what you said. Let's just race them around, see what happens. It's kind of the DARPA race, but now for DIY or for the new companies. And NVIDIA is sponsoring a F1 racing, autonomous racing league.
So that sounds fascinating. It sounds like fun. So I think that we're getting to the end of our questioning. I did have one example that seems, I think, time relevant, and I think maybe in the past month, if anybody has seen this, but somebody from Volvo was on YouTube or another platform ranting a little bit about the lane markings situation in the US, and specifically at times the lack thereof, and wanted to ask, what do we do in transitional areas with no lane markings, or areas where lane markings are scarce? just to reframe the question a little bit back more towards the technical side and how you will actually allow the AV to operate.
Yeah, I don't know that they're that they're that bad. I guess we have places on our route on like the 280 that came through and they repaved and they just never bothered to repaint lane markers. Yeah, I don't know. I can't really speak to other countries, but it depends on context and what other cues are around for the vehicle. We don't drive 100% off lane markers, and I don't think we should expect the AVs to either.
Okay.
I think it's a good point. The maps are often wrong, but reality can be wrong too, in the sense that it's either ambiguous or just two rules apply at the same time, and the sensors say, well, there are 2 lane markings, they are 15 centimeters apart, I'm going to squeeze my car into that. That doesn't work. And so the reality can be wrong. And so all the sensors inputs have to allow for wrongitude, and the planner has to make decisions about what to do in that case. And maybe the other cars, either historically, if such a trajectory average exists, or right in front of you, if you can see another car in front of you, can serve as an alternative sensor in that context.
Okay.
Specifically over like on 880 going towards Oakland, there's a place like where you've got 2 sets of lines that cross like where they repainted the new lines, and that's one of the situations where you could not trust the lane markings to help you navigate that situation. But luckily the sensors that we've got on these cars these days are pretty good at being able to not hit other vehicles that are moving at roughly the same speeds, like towards, and they can adjust their velocity, and they don't have to rely on those sorts of things. So.
Of course, it's like the Blue Angels. If the first one drives into the mountain, but I think that the bar is that you can't assume that governments will have the money or political will to repaint the streets just so that we can have more autonomous Ford cars on the road. It's just not going to happen. Okay. The cars have to be good enough to treat all the situations that the humans would treat reasonably, at least as well.
Okay.
And, just like you have, if you go to your cell provider, they have coverage charts. You can imagine another layer of this map data might be levels of like. I don't know what the right word is, like quality of
your Uber doesn't go there.
Yeah, your cars will not autonomously drive there. Maybe certain areas that they did not have good enough data to be able to operate in. Unless we had cars that could operate autonomously so well, they didn't need map data. So.
That's actually a good point. So we have one company we just funded that, a little bit of self-advertising, but that does campus transportation on private campuses, and so it doesn't fall under the public NHTSA and other rules. And so we think that they can go to market fast. It's a very different route planning problem because they have, think of university campuses or manufacturing campuses or resorts or things like that. And so there are a lot of people. Everything is slow speed, but very unpredictable because people can change direction almost at a moment's notice. And on the freeway, that's just physics helps you a little bit there. So different planning and different legal regime there, but you stay away from public roads.
Okay. I wanted to I've got a few more questions. One being specifically, what obstacles are in your way of route planning right now? Specifically, it's really curious for you because you're not quite there yet to the point of getting your route planning, and maybe just list the challenges that you have ahead of you into actually moving into actualization.
So definitely for us, it's the cost of sensors for underwater applications. Like I said, the cheapest side scan sonar system you can buy for doing a 2D scan costs, or actually you can do 3D by actuating it again, it costs about $8,000, which is 8 times the cost of our vehicle. So that's definitely one giant barrier, and there's a lot of other sensors that could be helpful too. Even altimeters, relatively, most like the Garmin altimeters and stuff like that you can buy for your boat for fishing cost in the order of about $100, and the software interfaces for those aren't like readily available. Like in the rest of the maker movement, you've got all these sensors that have like open APIs and work with all these Linux single board computers. That just doesn't exist for a lot of the sensors that we need for underwater navigation. And so we're trying to work with some of these companies like TriTech and other people to see if is there a way that we can create maybe not a highest resolution sensor, but maybe something more affordable that we can start getting better state estimation data on our robots so that we can actually do some routing and planning. So that's one thing. Better cameras are definitely useful for us. so the advent of like these H.264 webcams, that's basically what we use for our onboard robot. We can use really cheap compute modules and have all the encoding done on like vendor-provided OEM chips. And so that definitely helps us like to accelerate the process of being able to get good quality data and do things like photogrammetry and any kind of like vision processing, whatnot. Also, even just like the Wi-Fi technology, being able to connect to that topside buoy and have accurate GPS data, and also 3G, 4G connections, we can find out a lot of information about where we are, and send do processing over the internet to do much better estimate, like basically pipe all of that SLAM processing off of the robot up into the cloud if we have an internet connection, and get really good estimates and like compare against other maps that are already out there. All those types of like data challenges and processing challenges are kind of some of the things we need to solve. Like I said, controls for the most part it's not that difficult a problem for us. Most of our obstacles underwater are try not to get your tether caught on things if you're flying with a tether, which is most of the use cases, and otherwise it's like don't hit the coral reef. So definitely in the field of vision, I kind of split our problem up into a few different types of autonomous routing. You've got, I want to fly a transect, so in that case you need a good accelerometer gyro combo and be able to nicely estimate, and even then you've got the problem with the currents. So we augment that with the topside buoy, which has GPS, and then we can fuse that data to kind of get an estimate of where we are, and then we can do transect patterns. The other case is doing a follow me, in which case having cameras, not just one, but having multiple cameras to have a constant visual estimation of where you are is useful for doing like tracking a fish, or you can even imagine like people use the drones to like film themselves while they're doing like snowboarding and whatnot. Divers actually want to use this technology to film themselves while they're diving, and also like carry things for them. If they want to go cave diving, they can bring the drone in with them. You can imagine if they have trouble, they can send the drone back out. So there are definitely some really interesting applications and use cases for this technology, but the sensor cost barrier is just extremely high. Once we actually have working sensors and we can get good state estimation, then actually we can do a lot of amazing things underwater.
It's a pretty long wish list, Charles.
We're making progress.
Have you done a fish follower controller?
We are working on that like right now.
Oh, really?
Yeah, I think a problem for almost everyone is going to be compute, and anytime you can save that, you're actually saving gasoline. In a lot of cases, you know, by bringing down the number of processing cycles, and that's what's so great about maps, is that you probably have a potential answer sitting right there in front of you, and you know, if you check that one and it looks good, that just saved you a lot of energy.
Yeah, I think sensor costs for the automotive world at least is coming down. The LiDAR sensors, the camera sensors, the mix of sensors for different classes of vehicles will obviously evolve and change. I don't think cost is really the biggest issue. Two kind of market-driven constraints that we'll see how it plays out, but they're interesting. One is the crowdsourcing of map data. To date, the big mapping companies were basically, Waze is maybe the exception, but they're driving fleets of very expensive mapping vehicles. They have lots of highly calibrated sensors and GPSs and IMUs on board. And now that cars basically are becoming talking machines that have a lot of sensors on them, and they can call back, the means of production of the data is now in the car maker's hands. And so that changes the dynamics of who has control over that stuff. So you can imagine that there will be a time at some point where Ford basically sends data that's map relevant, and whether that data is processed by Ford locally or by Civil Maps or whatever, it doesn't matter. But it gets sent up, and that data is now available like a marketplace, like the New York Stock Exchange or the Chicago Mercantile. And that data can then be basically auctioned off to people who make maps or make other things. And some of it will be relevant because it is a type of data that you really want, like LiDAR data, Precision 3D, or because it's very, very fresh, or because it's covering a lot of, Jaguar makes a few cars, so they maybe don't create as much map data, but VW or Ford create a ton of map data. And so that could be almost like a BARDA system where the people who aggregate and create and clean these maps give a discount, or there's some quid pro quo for getting map data out. That doesn't exist today, and I don't think the business models for that exist today. But that'll be an interesting thing. And in the car world, of course, business models for barter exist. And then the other thing is the way that sensor integration is done. Typically, the car world has a very deep supply chain where the car maker buys things like controllers and sensors from other people like Continental or Bosch or Denso. And then these guys buy their cameras from yet third people. And so the car maker gets the control unit for the pedestrian detector, let's say, from Continental, and then that thing spits out over the car bus, hey, I see something in front of me at 20 meters moving left at 2 meters per second. That could be a problem. And so that high-level data is then shared with the planner. And at the moment, that's kind of how things are being architected. Correct me if I'm wrong, but that basically each sensor modality has its processing done by the supplier of the sensor. But that's not the optimal way to process things, because you throw away a lot of data and you don't use combined data where, for example, the video has corroborating evidence that there is something in front of you when the LiDAR says so, or the radar and so forth. Mm-hmm. And so you really want to bring all the raw data together and process it together and then spit out the fuse data. That's being done, and that's why people like Continental and Bosch are buying sensor manufacturers and doing the fusion themselves, but it changes the power dynamics, because today Ford will go to 5 different suppliers and say, you have to give me this cheaper, or you have to give me this faster. And when the suppliers now basically sell you an integrated harness of everything, or they don't validate it, that puts a little bit more power in the supplier's hands. I don't know how that will play out. Maybe you have a comment on that.
Yeah, that's a really interesting question. I'm not sure about how it looks from a supplier standpoint, but the optimal solution would probably be to have a lot of very dumb sensors and one place where everything is getting aggregated. That would save information. Yeah.
From a technical point of view.
Yeah, from a technical point of view.
Yeah, I just want to touch on something interesting. Like you said earlier, the map is almost always wrong. And so when you have like one company that goes out with the specialized equipment for doing the mapping, they can get a very high fidelity map with their high cost sensors and whatnot. And that one snapshot is probably great. It can be used for a lot of situations like doing routing and whatnot. But one thing that it doesn't have is that temporal aspect that I told you about maps earlier. And that if you've got Ford out there with 1 million cars that all have these sensors on them, and they have basically every time a car drives by an empty parking spot, that is detected and compared in the map. It's like that if it has that connected model of a map that you're connected to the internet, that information can be fed back up, and you can have an app on your little dashboard that's basically saying you can have like a live free parking space. So that kind of stuff isn't possible when you just have like small map, because they'd have to be driving out there every day with fleets of vehicles. So when the vehicles themselves can do those types of things and provide so much of this extra temporal data and like contextualized metadata about the environment, a lot of new things are like opened up in terms of opportunities for routing.
Yeah, I think it's a very symbiotic relationship between maybe a little startup and a large company. If they do business differently, they can really speed past the old model of having a fleet collect data.
All right, thank you for those technical answers. I want to end on a more light note, and not everybody has to answer if you don't have a story, but I want to pull you guys. Do you have a time when route navigation has failed you?
So my first encounter with this was my first time that I actually at NASA. I was working on an aerial drone. I had taken one of the Pixhawk microcontrollers that fly the 3D robotics drones and kind of hacked it by feeding it a false GPS data to do a positioning system with like those positioning infrared cameras around the room. And it was a traditional case of flipping a sign. And this it was one of those quadrotors like with the dual rotors, so it could probably fly about 80 miles an hour. It just shot straight up. Negative feedback loop just kept positive feedback loop kept piling on the velocity, and it just shot straight through the roof, knocked out all the panels, shards of propeller blades flying all around the room, sticking into foam things. That was my first experience. Like I was like, this code's probably going to work the first try. I've simulated it. I've run the numbers through it. You put it on the vehicle, and something as simple as like this negative sign just sends it straight through the roof.
Who paid for that? Well, you're in good company. I remember when the F-15 navigation system first came out, when they first flew it over the equator, suddenly the pilot noticed without doing anything that his plane was upside down. maybe a more local apocryphal story from one of our startups. I won't say which one, but they're doing, well, actually it's obvious, you can figure it out, but they're doing current route planning relatively simplistically based on just the static environment. So every frame they take basically a picture and a LiDAR and so forth, so they integrate that and they have an image of what's around there and they go, okay, I'm going to go around obstacles. Maybe I told this story before in the same forum, sorry if it's a duplicate, but it's just funny. And so they go, oh, if there's an obstacle right in front of me, try to go right. If there's nothing there, go right. Otherwise, then go left. Okay, so they do that. So that works fine when the CEO does a demo for us, are we going to invest? Oh, let's see. And so he stands there, and the thing goes around, and it's great. That works really great. And then school lets out, and half of Santa Clara University suddenly, all the guys are on their phones listening. Nobody cares about this golf cart they drive around all the time anyway. This one happened to be self-driven. They didn't notice that. And so they don't pay attention. And so there's this one woman walks across like this, and the car comes up to it, and the system goes, oh yeah, there's an obstacle, let me go right. And she goes, of course she keeps going right. Oh, there's an obstacle, let me go right. And so we were going like this until we were an inch away from her. She didn't even notice it, but I'm like clenched. And he goes, no, don't worry, we'll stop at the last minute. And it did, but so that's a problem where the router didn't actually take dynamics into account, which of course, most routers will do. But anyway, it's a little story about when route planning can go wrong.
Mine was more human error. It was when I had just moved to the Bay, and I was running late. I was supposed to drive up to Portland to meet my girlfriend, and so I got over into East Bay, and I had no idea what I was doing. So I figured that I should just get the in-car navigation system going north because there was way too much traffic for me to be looking at my phone all the time. And I had somehow lost my suction cup thing. So my car will only let me say a city name if it's in the same state that I'm in. So it says in California, say the city name, and I only know one city in Northern California, and it's Eureka. So I put that in, and my trip took about 6 hours longer because I was on the what is that, the 101?
It was very scenic, though.
Yeah.
Redwoods.
It was beautiful.
Beautiful.
When it wasn't pitch black because it was the middle of the night. Yeah.
All right. Well, thank you for sharing those stories. I guess, should we open it for questions? Yeah, does anybody in the audience have questions for our panelists? Nope.
I have questions mostly for you, John, but the model of having a central processor that does all this stuff is great, unless you're trying to build a range of cars, some of which are fairly inexpensive, and you can't afford to put that expensive processor in the low-end vehicles. So how do you sort of trade off that value of that central processor versus the practicalities of building multiple models of cars at multiple price points?
That's an interesting question. I guess for the I guess it's you can't half do level 4, right? It's not like you divide level 4 in half and you get level 2. So yeah, if you're gonna do it, you have to do it, right? As far as the level 2 stuff goes, I would just say you just end up with fewer features if you're on a cheaper platform.
How CPU bound are you today? Is it a problem trying to find CPU platforms that consume little power and do the stuff that you need, or is it not a problem?
So
free scale boards?
Yeah, so thankfully that's not my job, but we do have a team in Palo Alto that's working on it.
Because I know NVIDIA comes out with these huge boards,
Yeah.
but are they automotive kind of priced and powered? They advertise them as such.
Yeah, we're evaluating them and we're evaluating others. So we'll find out soon.
All right. Any other questions? Yeah, sure.
So how do you verify the accuracy of these global maps at all? It doesn't seem to me apparent that you can verify if you want to have 5 centimeter accuracies, and some of those people claim that. How do you verify that your maps are globally accurate to 5 centimeters? I mean, is there any way of doing that? I mean, it doesn't seem.
I don't think they make an absolute claim of 5 centimeter accuracy. It's 5 centimeters within the lane. So it's if you know you're on that road and you're on the second lane, you're 6 inches or whatever metric off in that lane. Is that true? You should answer that question. It's not absolute accuracy.
No,
on the
I
world.
just drawing from my mapping background. I think that some amount of ground verification has to be done, and potentially, I can't really speak directly to how we do that. I'm still somewhat new with the company, so.
But
Shrevin?
other-
Sorry. Anybody in the audience have any way to respond to
Yeah.
this?
So there's a difference between like precision and accuracy, right? So precision is about if I'm looking at something and it's in the relative context, then you have the relative precision too. Like, can I correct the GPS position and consistently overlay the map data onto what I'm seeing? And then you have absolute accuracy, which is georeferencing accuracy. So if you have a particular point, how far away from that point are you if you're sharing intelligence between systems? The general rule of thumb is, sharing information between systems is not at a tactical level, but it's more at a strategic level. So if you have like 1 meter resolution, it's sufficient. But when you're dealing with low-level control, you need to be at the sub-decimeter level. So that's where the relative localization comes into play. And that allows you to use the context from your map data to make decisions. And that's at the tactical level.
Does that answer your question?
Somewhat. So the other question I have maybe is, everybody talks about high definition maps, you need those. Apparently a human driver doesn't need those, right? So is that maybe the whole thing a dead end thing with this highly accurate, tediously collected data? So can you actually say maybe you really don't need it, it's just that the technology, perception technology is not at this level yet, but eventually you don't need these maps, and you probably can't even build them for everywhere in the world, right? That's not feasible. So what's your point of view on that?
Do you want to represent the company point of view?
Well, I would argue that we do need these maps because if you want to advance the technology, which it sounds like everybody is moving in that direction, then it's certainly not a dead end, and that it's a valuable effort to pursue. And I don't know what the alternative would be. So that would be my response.
Well, the
Just
alternative
not-
is like a human driver
But
doesn't have those maps, right?
So
apparently
just-
it can solve the problem.
Yeah,
without-
actually, those are two kind of diametric philosophical approaches.
Yeah.
And during the first DARPA challenge, I remember Sebastian Thun's team basically said, we're going to just take sensor data and we're not going to have a map at all.
Okay.
And Team Red, which was the CMU team, said, oh, we have all our stuff based on mapping data. And they scrambled because they changed the route the day before. And so they were all like in there trying to do that, and they didn't get it finished. And that was a problem. I think those two are not mutually exclusive. I think that you have to do better than a human. As an autonomous vehicle, if you're only as good as humans, we kill 35,000 people a year as humans, we should be able to do better with autonomous drive vehicles. And so things like you're coming up to a dangerous intersection, you should probably preemptively slow down a little bit because there's often kids at 12 o'clock at every day, except Saturday and Sunday, crossing. That's knowledge that can be in the map that can reduce the last minute collision avoidance kind of maneuvers and be in the tactical planner. And there's a lot of risk scenarios where you slow down. Even today, I think that Waze will give you warnings when there's an accident coming up or a traffic jam coming up. So I think that with maps, you can do better. I don't think you can rely on maps alone. I don't think anybody's making that claim, but it's an augmentation. It's an extra sensor that can do more than what a human could do.
And I would say that yes, there's probably a diminishing return with like spatial data, like how fine a precision do you need? Like, do I need to have like millimeter accuracy of my map? Probably not, because that millimeter won't really buy you anything because you're gonna be acting off of active sense data anyway. But what you're gonna see is like these maps will evolve to have more data than just spatial data. You're gonna have all this temporal data that's coming, made about behaviors, when things are happening, that sort of thing. Like children, like schools between these times. That's the kind of data that's gonna be compiled like further and further into these maps to make them more advanced. That are really going to like affect the behaviors of these autonomous vehicles, not just like making things finer and finer precision on the spatial scale.
just another example. I drive home every day over a mountain hump, and if I drive home at night at 5 o'clock, I have exactly the sun in my eye as I come. So I come from very dark into very bright, and I can't see anything. If you can know that in advance, you can basically tell the controller can say, I'm going to start mistrusting a huge whiteout in my video sensor in a second because it's the sun. I expect that, and that's just helpful. And the human has, you know, the wet wear is a few hundred milliseconds, but that may not be enough to avoid an accident.
What do you know about Google's philosophy with this question?
We lack a Google representative, apparently. Richard?
I have one last question relating to vehicle tracking when it comes to route planning and when that becomes useful. Obviously, at the moment, we all have different driving styles, and if there were all autonomous vehicles on the roads, perhaps we could set different driving styles and utilize the vehicle in front of us to understand whether or not we should make a certain path or not. If you're following people, maybe there's a guy driving his Corvette 90 miles per hour around the corner, and maybe that's not the best path for you to take in an autonomous vehicle. But I guess my question is when that becomes helpful to have that vehicle tracking, how many autonomous vehicles need to be on the road for that to become useful, or if it's going to be more prohibitive than useful until there's a critical mass?
Yeah, I don't want to monopolize this.
Yeah, I think any information is helpful when you can say this is a potential vehicle trajectory. Whether you do it at the same speed and with the same amount of side slip is is up to you. But yeah, additional information is never going to hurt. But to the point of like what happens when every vehicle is autonomous. I think that's where it starts to get really interesting, because we might not, you might not even understand anymore how the vehicles are moving and how they are doing their motion planning. Not that it wouldn't have been programmed by a human anymore, but just that what is optimal in that situation might look completely different from the way traffic works right now.
And one thing to add on to that is kind of like a side note, but like so in the airspace right now we have something called ADS-B. I can't remember exactly what it stands for, but basically planes have to broadcast their intent to other planes surrounding them. So that's for the most part it's the pilots rely on that data. But one thing I know NASA's experimenting with this is something that was popping up right before I left. They're trying to do experiments where they can have all the autonomous vehicles broadcast their intents to each other over near-field communications and over internet, that sort of thing. And when you get in that situation where all cars are autonomous, you take on the security risk of now the cars are interconnected, and then you have like certain situations where you can have bad actors broadcasting false data to force certain situations to happen. But when you have that capability of having all the cars broadcast their intent to each other and feeding directly into each other, like not directly, but like having that available as a source of information going to their control loops, then pretty much traffic I think would entirely disappear in terms of like or collisions and that sort of thing would disappear, because their control loops are getting pretty good to like if they had like perfect data about what each car was going to do, then that kind of solve that problem.
Yeah, I think our current perception software, I mean, there's multiple steps. The one I described with we're almost driving into the lady, that was, too little. Most perception software today will do, I see an obstacle here and it's moving and it has basically a vector and a speed. In future, and I don't know how long it'll take, but I think it will be very useful, and there are actually neural networks that can do this too, to deduce not just state, but behavior. In other words, what is the intent of the driver in front of me? And certainly putting a turn signal on helps me, but if I see a driver in front of me going like this, I'm going to back off. I'm not going to follow that car very precisely, right? Because I know that there is they're drunk or they're doing texting, and I'm going to back off a little bit. And that level of what the intent or behavior of other people in the perimeter of a car is, I don't think current perception software does that. It doesn't do behavior. It does like current state and position and maybe a trajectory vector. And the mid-level planner, a tactical planner, should really take that into account. And we don't have the perception software for that at the moment. And the other thing, I've seen the traffic simulation of all autonomous cars crossing a 4-lane intersection. without a traffic light, and they basically, it's just computers, right? You can cross. Now when that looks fine from above, looks really good actually, they never crash. And then you put yourself inside a car, and you have a 3D simulation inside that car, and your pants are not going to be the same when you leave that in the city because you see other cars coming like this. So there's, I think we will limit the envelope of what our autonomous cars can do for the foreseeable future, or we have to have dark shades.
All right, well, thank you. Unless there's any other questions, I think that we'll call it an evening for the panel discussion, and I think that we can all hang out and network and socialize a little bit longer if you'd like that. Thank you.
Thank you, Civil Maps.
All right. Hi, my name is John Mullen, and I'm a research engineer at Ford Motor Company. I'm working on level 2 automation, and routing is important for me to understand how we can use geographic information to add context to automated systems.
I'm Charles Cross. I'm a software engineer at OpenROV, and in the autonomous vehicle routing domain, our robotic platform. So with our underwater robot, we have an internet-connected platform. Basically, anyone can control the robot from across the internet. And one way that routing is important to us in terms of autonomy is that the latency between the person across the world who's controlling this robot is sometimes unmanageable to the point where they're not actually controlling the robot the way they expect. So having autonomous routing capabilities and being able to fly autonomous patterns enables people from across the world to fly the robot in a manageable way.